Welcome, Chemistry 1007 students at ULM. This is Dr. Pryor. We are covering Chapter 9. We're still going into electron domain geometry and then molecular domain geometry. Please review the last video. We talked about the first thing you want to do is figure out all of the electron domains. Then you will know for whatever number of electron domains you have, you will know what the electron domain geometry is. However, then you could have non-bonding domains or electrons that are lone pairs, and you will then have a different molecular geometry, even though the electron domain geometry will remain the same. So let me show how that works. For example, we did linear earlier, which was two electron domains, and we see the last video for that one. Here we go to three electron domains. So the EDG, or the electron domain geometry, here is always going to be, for these examples, this is the EDG, right? That's the way that we abbreviate it. And we have trigonal planar when there's three electron domains, whether they're lone pairs or bonded electrons between two atoms. This is, of course, is a central atom. We can go through this table, and we could have three bonding domains, zero non-bonding lone pair electrons, so we have no lone pairs on the central atom. And we have to think about it's all relative to the central atom. We're talking about the lone pairs on the central atom, not the peripheral atoms, just the central atom. How many lone pairs are on the central atom if we're talking about non-bonding domains that belong only to the atom and not to the molecule? Or, yeah. So we have trigonal planar, which is the molecular geometry, which is the same as the electron domain geometry. We have no lone pairs on the central atom. So, for example, boron trifluoride would be trigonal planar, 120 degrees for the dihedral angle. Remember what a dihedral angle is. I explained it in the last video. So now let's suppose we go to something that does have three electron domains. They didn't write this in here because it's assumed to be the same. The electron domain geometry is not going to change. It's still going to be trigonal planar, but now we only have two bonding domains and one lone pair on the central atom. That's going to change the molecular geometry because we cannot count the lone pair as a point group. We have to say that it's not there. So now this trigonal planar electron domain geometry, when we look at the molecular geometry, it's going to be bent. And an example of this is NO2 with an anion, and it's bent clearly when we just look at the molecular geometry, which is different. The molecular geometry and the electron domain geometry differ for this one. Okay, so let's look at others that have 3, 4, 5, and 6. We just looked at the one that has three electron domain geometries. We have the possibility of tetrahedral as well, where there's four. We have electron domain geometries. We have trigonal pyramidal, where there's going to be a possibility of five. And then we can have bent. Oh, no, I take that back. This is when we have four electron domain geometries. Four electron domain geometries. These are all the same electron domain geometry. We're talking about four now, but there's three possible different molecular geometries. So anything that has four electron domains is all going to be tetrahedral with respect to the EDG. But when we look at the molecular domain geometry, or the molecular geometry, we're going to have to ignore lone pairs of electrons, and we come up with different molecular geometries. And let's go through the table, and it'll help us. So a four electron domain molecule such as methane is tetrahedral with respect to both the electron domain geometry and the molecular geometry. So EDG in this case equals the MDG, right? But with these other two, not the case at all. The EDG does not equal the molecular domain geometry. They are not the same. And we'll see why as we go through this table. We can have three bonded domains. We would then have a trigonal pyramidal system. We could have where we have only two bonded domains and two lone pairs. We would have water, which is bent. So let's take a look at this. So for this example, we have four electron domains, four electron domains, four electron domains. All of the electron domain geometry is the same for all of these molecules, which is tetrahedral. But the bonding domains for the first one, we have four of those and zero lone pair bonding domains. So we have a tetrahedral structure, and the good example of that is methane. Now we go to a situation where we have four electron domains as before, but now we only have three bonding domains, and we add one non-bonding or lone pair instead of a bonded group. And now we have a trigonal pyramidal molecular geometry. Different electron domain geometry versus molecular geometry. An example of that is ammonia or PCl3. NH3 or PCl3. Then we go to a situation where again we have four electron domains. We still have the same electron domain geometry that did not change on us. That's tetrahedral, but now only two of those domains are bonding and two of them are non-bonding or lone pairs. So we have two lone pairs that cannot be counted as having any groups. So we only count the 2 point groups here, and we end up with a bent molecule, and water is a good example of that. So you can see now clearly for two of the three here how the electron domain geometry and the molecular geometry are different. Here's an example of the dihedral angles and how lone pair electrons repulse greater and cause the angle to shrink. And two of them causes the angle to shrink even more because these lone pairs are more repulsive than these bonded pair electrons, right? So that is how we explain that. We could also think of the volume or shape of these electron domains. This is a bonding electron pair, and this is a non-bonding lone pair of electrons. There would be, of course, two electrons in there. And so the non-bonding lone pairs are physically larger than bonding pairs and taking up space. So multiple bonds and bond angles, kind of the same, a little bit like lone pairs, but they are not lone pairs. Double and triple bonds. Here we have a double bond, right? We have a sigma bond at lower energy, and then we have a pi bond at higher energy, and that composes a double bond. And the double bond is a little bit more repulsive than a single bonded pair of electrons. So it repulses and has the strength over the single bonded pairs and repulses these single carbon chloride bonds. These single carbon chloride bonds are suppressed a bit because of this, which is called a carbonyl, right? A carbonyl, which is a very useful functional group in organic chemistry. It's called a carbonyl group. And so we can see the difference in the repulsive effects of a double bond versus a single bond. And the carbon here, of course, has what? Carbon here has carbon has no lone pairs of electrons. Oxygen does, but it doesn't matter because oxygen is not the central atom. We only have to worry about carbon and determine the molecular geometry. This is trigonal planar, of course. So some elements, now we're kind of mixing some things because remember the Lewis structures, and then we have the octet rule, but the octet rule can be broken by certain atoms, especially the D transition atoms in boron, which doesn't have to fill up its entire orbitals. But d orbitals add extra orbitals, and it just makes sense that what is the octet rule will later become more like a 18 electron rule, but we're not going to cover that here. Oftentimes it takes 10 electrons. Some of these structures should probably just be best memorized. And so we have where we could have 5 electron domains. Let me change to a pen and change color, change ink color. And so we can change, we can have 5 electron domains and 6 electron domains, and then we can look at what happens when some of those electron domains are lone pairs or non-bonded electrons. Uh, for those with 5 electron domains, that will always be trigonal bipyramidal, which is 2 3-sided pyramids, base to base to each other, one upside down, one right side up. We can have 4 different possibilities. We can have trigonal bipyramidal, seesaw, T-shaped, and linear. This is all for the molecular geometry, not the electron domain geometry. The electron domain geometry is just one type. It's trigonal bipyramidal for all of these. The rest is just molecular geometry. Okay, so there are 2 types of positions when we think about a trigonal bipyramidal electron domain. We can look at the axial positions, which just like as a ball spins on its axis, the Earth spins on its axis, it runs vertical. So we have the axial position. It's the vertical position. But then we can also have the equatorial position, and that is going to be more horizontally, right? So just like the equator, it's going to be equatorial. So, but what happens when there's not a real atom here? It's not, there's no point group. And we start replacing these atoms with lone pairs of electrons. That's where we get changes in the molecular geometry. The electron domain geometry, it stays the same. So the electron domain geometry for all of these with 5 um, electron domains always is trigonal bipyramidal. So once, remember, we should determine the electron domain geometry first. Then we need to figure out how many of those are bonded. And in this case, there's 5, then there's only 4, and then there's 3 and 2. And those become replaced with lone pair of electrons oftentimes, 2 lone pairs of electrons, 3 lone pairs of electrons. And that will change the molecular geometry for every single example here. In the first example with 5 electron domains and all of them are bonding domains, the electron domain geometry remains trigonal bipyramidal, and the molecular geometry does not change, and it's trigonal bipyramidal. An example of that is PC is phosphorus pentachloride. Phosphorus pentachloride. Okay. Now we have another situation where we have 4 bonding domains, but now we have 1 lone pair of electrons. And that is best exhibited in the sulfur tetrafluoride, which gives us a seesaw for the molecular geometry, a seesaw just based on that there's 4 point groups, and the other one no longer counts because it's just an electron domain. We don't count lone pairs of electrons as point groups. Then we go to bonding domains. There's only 3, but then we now have another added non-bonding domain to go to 2. So now we have 2 lone pairs of electrons that turn this into this T shape. And we look at chloride or we look at chloride trifluoride as an example for that. And so the molecular geometry is changing for every single one of these. And then we end up with only 2 bonding domains and 3 lone pairs or 3 non-bonding domains, which end up taking the entire equatorial positions up. And we have a molecule that actually looks linear, of all things. And we have this xenon difluoride molecule, which is very weird in the fact that, noble gases are usually pretty non-reactive, but they can make this one. And again, interesting stuff. We come to the final example. The octahedral electron domain has to have 6 electron domains, but it has other molecular geometries on top of it, all sharing the same electron domain geometry, all being shared, but the molecular geometries will change due to an introduction of lone pairs and the loss of point groups. Octahedral is one of the shapes, square pyramidal and square planar. What does that look like? Well, we have 6 electron domains for every one of these. They all are going to have the same electron domain. It's going to be octahedral for the electron domain. That's not going to change. But what will change is the bonding domains. In the first example, we have 6 bonding domains and no non-bonding domains, and we get an octahedral complex, and that is sulfur hexafluoride. And the electron domain geometry and the molecular domain geometry remain the same. But in this next example, we only have 5 bonding groups and then 1 non-bonding group. So we replace a point group with just a lone pair, and we can't count that in the molecular domain structure. And we only have 5 point groups, and this gives us a unique square pyramidal structure for the molecular geometry, even though the electron domain geometry remains what? Unchanged. It's still octahedral. An example of a molecule or a complex that does this is bromine pentafluoride. Very interesting having 2 halogens bind together. This is really cool chemistry that we're not going to talk too much about the orbital molecular theory. Just know that it is possible. You can imagine bromine has probably got some d orbitals, but there's other things going on there. So here we end up losing another point group, and we replace that with another lone pair, and we end up with this square planar complex where we only have 4 point groups that all end up being what you could call equatorial, and the axial groups are replaced with lone pairs of electrons. And so this is flat like a pancake, like trigonal, like a trigonal planar would be, but that's a different EDG. This is xenon tetrafluoride, and now we still have the same electron domain geometry, but a different molecular geometry. So know where that comes from. VSEPR also can be used, and this technique can also be used to evaluate each atom that might be a central atom onto its own with regards to the entire molecule. Now we have really 3 geometries because we have 3 atoms we can kind of identify as being a possible central atom in its region. So we have a larger molecule. These are larger molecules with more than one stereo center, so to speak, or should I say more than one geometrical center. Where, for example, over here, we can look at this point, this carbon atom, and its electron domain geometry is going to be tetrahedral along with its molecular geometry. Carbon has no lone pairs, so the electron domain geometry, which we have to solve for first, is tetrahedral. Since there's no lone pairs, it's going to be the same for the molecular geometry. It's all tetrahedral. Now let's go to the second carbon atom from the left, which is central, and it's bound to this carbonyl. Remember, I talked about a carbonyl, which is a carbon double bond oxygen with a pi and a sigma bond. The electron domain geometry here, it has 3 domains. This counts as 1, 2, and 3 electron domains. There is no lone pair on carbon, so the electron domain geometry is trigonal planar, which is flat like a pancake, and the molecular geometry is trigonal planar. Remember, we also saw a square planar earlier. That's another flat molecule, but it has a different electron domain geometry. Now we're going to look at the third atom in this molecule that might have geometry, and we're looking at an oxygen bound to a hydrogen and a carbon. And so the electron domain geometry, there's also a couple of lone pairs here. So there's 1, 2, 3, 4 electron domains. So the electron domain geometry for this oxygen is tetrahedral, but the lone pairs cannot be counted as point groups, so we have to only count the hydrogen and the carbon. So there's only 2 point groups attached to this oxygen. And so the molecular geometry is simply bent here at this oxygen. So now you can see where it gets a little more sophisticated. This was acetic acid, CH3COOH. It's a weak acid. It donates a proton in solution, household vinegar. So in summation, going back, and we'll get to this polar idea in a second, to be able to do this electron domain geometry, first you want to draw the Lewis structures by figuring out all the valence electrons plus the charges in any molecule. and draw the Lewis structure. Then you want to spread out all the electron domains as far away from each other as possible with respect to the central atom. So then you want to count up the electron pairs that you have, and that will be the electron domain geometry. Then you want to eliminate any and then you want to get the geometry, the electron domain geometry with all of the electron pairs that are attached to the central atom, or all the domains that are attached to the central atom as we went through. Figure out the geometry. Then you want to look at the molecular domain geometry by eliminating any lone pairs in your molecular, in your deduction of the geometry, minus the lone pairs as point groups. Now, distinguish between bonding and non-bonding electron domains. Make sure you can do that. That's the only way you're going to be able to figure out the molecular geometry. It could be, now, an electron domain geometry and the molecular geometry can be the same, or it can be different. Okay, so what's next on the agenda? How do we determine polarity? We're going back to Linus Pauling and the electronegativity scale and thinking about how electronegativity increases going left to right to fluorine, and electronegativity increases from the bottom going to the top of the periodic table. So a polar molecule or a polar bond, just think about a bond. Let's not think about a molecule yet. Let's just think about the polarity or non-polarity of a single bond between two atoms. We need to find out if the bond even has a dipole, and then we have to look for other bonds within that atom. And sometimes we may have nonpolar bonds which have very little electronegativity difference, like carbon and hydrogen. And then we can kind of figure out from all the bonds within this molecule, what is the overall likely direction? Is there any directionality where the electrons are distributed to one part of the molecule and the electrons are lacking in another part of the molecule because of the dipole and the ability of the individual atoms to attract the electrons? So here is an example where if we look at just carbon and oxygen, guess what? We have a dipole. The electrons get pulled towards the oxygen. Clearly a dipole, 3.5 and 2.5 is 1. That's a dipole. But then on the other side, we have carbon, and then we have, let me change to the laser. We have another oxygen, the carbon and oxygen, and it's the same type of bond, and it's a 1 as well. And guess what? It's linear. So what happens is the dipoles get canceled out. So even though there's a dipole, there's a bond in here that's polar, and there's a bond here that's polar, the overall dipole is 0. The molecule has no polarity. It's considered non-polar. Now, let's take a look at water, everybody's favorite molecule. We have oxygen here and hydrogen, and each hydrogen and oxygen bond, the electrons are shifted towards the oxygen. The oxygen gets the majority of the electron density because it's more electronegative, by even more so than carbon and oxygen. It's something like 1.4 for each of these bonds. And we add this all together, and we don't have to do the math here per se. This is more of a qualitative judgment. The overall dipole of the molecule is towards the oxygen. So the oxygen has the electrons, and the hydrogens are lacking in electrons and are partially positive. So there is an overall dipole to this molecule, which is 1.85 dBi. dBi is a way to measure the dipole moment in the molecule. So we have dipoles, but then we have dipole moments. Dipole moment has to do with the entire molecule. A dipole, a bond dipole, is just within a single bond between, or a double bond between two atoms, or even a triple bond. This diagram, if something is very red, that means it has electron density. If it's blue, it has almost 0 electron density. And green is kind of like, it has little electron density. And this dipole moment is canceled out by two oppositely directed bond dipoles. But here we don't have, it doesn't cancel out completely. And so there is electron density all the way towards the oxygen, and here at the tips, it's completely blue, lacking the electron density, meaning that this is partially positive. So if we were to write that, we would say that this is partially positive. This is partially positive, and this is partially negative, just as we would suspect. And there is no charge on water, but there are partial charges when we look at the dipole and the individual bonds. So water does have a dipole moment. Carbon dioxide does not have a carbon dioxide does not have a dipole moment. And uniquely, we can do this with different molecules, small molecules with just maybe one single central atom. Here, example is boron with 3 fluorides attached. Because everything is going in equally but opposite directions, there's a 1.5 dipole bond. There is a dipole to each of these bonds, but they cancel out. So it ends up being nonpolar. So it does not dissolve very well in things like water and acetic acid or something, or ammonia. It's going to be pretty much nonpolar. Now, we have another molecule which can be kind of confusing. It's carbon tetrachloride. Carbon tetrachloride. Uh, they have dipoles too. They're not real strong, but they're about 0.5. But guess what? They're going off in all 4 directions equally, and they end up canceling out to be nonpolar. So carbon tetrachloride doesn't dissolve too readily in water at all because it's nonpolar. Water is very polar. Now, the first 2 molecules we look at do not dissolve in water too easily. Now, if we take ammonia, NH3, we do have a dipole bond in each of these bonds between the nitrogen and the hydrogen. And they do actually give some directionality similar to water. So we do have sort of a dipole. And so ammonia is polar. It will dissolve in water. So keep that in mind. Polarity means it likes charged species somewhat. Things that are polar, like itself. Nonpolar and polar molecules tend not to dissolve in each other, right? Oil and water does not mix, right? So if we come over here, we see sulfur tetrafluoride. Again, 2.5 is the Linus Paul reading for sulfur, and 4.0 for fluorine, which is the most electronegative species on the planet. So fluorine gets the electrons pulled towards it, and this is not exactly equal. It doesn't cancel out, so there is some directionality there is a dipole moment for the entire molecule. So a dipole moment represents the entire molecule, which can be designated as U, and this has it. Then we have carbon, we have chloroform. Chloroform only has 1 chloride. If we took this carbon tetrachloride and replaced 3 of these chloride atoms with hydrogen, we would end up with carbon or chloroform. And chloroform is polar. It does dissolve in water. It would dissolve in ammonia. It wouldn't want to dissolve in BF3 or anything like a hydrocarbon. It would be insoluble in a hydrocarbon a little bit. So, but it is small, so that makes it a little bit uncanny. It can do some things sometimes because of its size. But this direction of the bond goes, it does have the bond between carbon and chlorine is polar. There is a dipole moment for the entire molecule as well. And so this has a dipole moment, making the whole molecule, of course, polar. So we have to think about the individual bonds, and do they have an electronegativity difference? And if they do, we have a dipole bond, but then we also have to think about the entire molecule and how the dipoles sum up. And then we can figure out the direction that the dipole might go in the molecule if one exists. Sometimes they cancel out. No dipole, there is no dipole moment in this one. There's no dipole moment, it cancels out. There are individual dipoles in the bonds from the polarity, but no dipole moment for carbon tetrachloride. Okay, that does it. Thanks. We'll be back with more for Chapter 9, some molecular orbital theory soon to come up, and we'll try to make that easy.